Humans possess a distinct anatomical configuration. We are the only species on Earth equipped with a heel bone that makes direct contact with the ground, a rigid, straight-ahead big toe, and a specialized longitudinal arch designed strictly for upright walking. This configuration bears a staggering mechanical burden. The average adult takes roughly 18 to 19,000 steps every day. Over a lifetime, that equates to 70,000 miles of travel, enough to circle the Earth nearly 3 times. This musculoskeletal model tracks the forces at play during human movement. Look at the force vectors acting on the foot. Every time the heel strikes the pavement, the ground reacts with an upward force equal to twice the person's body weight. When transitioning to a run, that localized pressure spikes to 3 times the body weight. That kinetic shockwave doesn't simply dissipate. It travels upward through a dense, interconnected assembly of 26 bones, 19 muscles, and over 100 ligaments, step after step. To survive this constant barrage of kinetic energy, the foot functions as a biomechanical paradox. It acts as a rigid, load-bearing support pillar for a fraction of a second, then transitions into a highly articulate shock absorber. Historically, the footwear industry has often approached this system with a flawed premise. Treating the human foot as a static mannequin or a stationary volume to be wrapped in leather ignores the reality of a dynamic, load-bearing linkage system. Advanced footwear engineering relies on a different operational sequence. Designers must act as foot fitters before they attempt to be shoe fitters. To effectively fit the foot, we have to deconstruct it. We need to break the skeletal architecture down into its 3 core biomechanical zones to analyze how each section manages incoming force. Natural anatomical variations, like an individual's instep height, the exact positioning of their toes, or the curve of their arch, alter how these 3 zones compress and behave under a heavy load. Aligning shoe geometry with these dynamic phases provides the structural offset necessary to mitigate common pathologies, like splay feet or hallux valgus. Let's strip away the muscles and ligaments to examine the baseline skeletal architecture, starting at the rear anchor point where the kinetic chain begins. This diagram maps the lateral view of the skeletal foot. We begin with the rear section, highlighted in green, the tarsals. Within this cluster, the calcaneus, the heel bone, and the talus serve as the primary points of initial ground contact. Their engineering function is straightforward but extreme. They absorb the concentrated shock of the heel strike, locking together to form the rigid rear pillar of the foot's longitudinal arch. Without the massive, dense geometry of these tarsals at the point of impact, the sheer kinetic force of a single walking stride would shatter the lighter, more delicate bones located further down the chain. Moving forward from the tarsals, we find the second load-bearing zone. This top-down view shows the 5 metatarsal bones, highlighted here in pink. Structurally, these 5 elongated bones serve as the physical bridge connecting that robust rear foundation to the forward toe actuators. Looking at the green bodies of these bones in this diagram, notice the outer boundaries formed by the 1st and 5th metatarsals. Together with the tarsals, they construct a weight-bearing arch that takes incoming vertical loads and distributes them horizontally across the foot's architecture. This horizontal distribution makes bipedal balance possible. It allows a human to maintain their center of gravity across uneven terrain and shifting orientations. Essentially, the metatarsals function as a structural suspension system, taking a localized, high-impact force from the heel and transforming it into a distributed load. At the very front of the foot lies the final kinetic zone. This chart breaks down the 14 phalanges, or toe bones, into distinct segments. Starting at the base, the blue proximal phalanges provide leverage required during push-off. Next are the middle phalanges, shaded in yellow. These execute complex micromovements, allowing the toes to physically grip the ground and stabilize the body's center of mass as weight shifts forward. Finally, the expanded tips of the pink distal phalanges bear the terminal weight of the stride. Packed with dense nerve endings, these distal tips double as a sensory feedback array, reading the ground. The toes operate as articulated actuators and sensory probes that govern the final propulsion and absolute balance of every stride. Now we can reassemble these three distinct static zones into a complete, functioning biomechanical engine. This kinematic model illustrates how these zones articulate together in a precise sequence to generate forward propulsion. Notice the propulsion vector at the top right and the rotational torque applied at the heel. As the red calf muscle engages and pulls the heel upward through this specific angle of the leg, the kinetic flow initiates. The tarsals absorb the strike, the metatarsals distribute the load across the arch, and the phalanges provide the terminal leverage to push forward. Because this is a continuously linked mechanical chain, restricting or misaligning any single component disrupts the entire sequence, forcing the knees, hips, and lower back to absorb the misplaced strain. A structurally sound shoe accommodates this fluid mechanical sequence, providing targeted support through each phase of the stride. To achieve that level of precision, modern footwear engineering has moved out of the sketchpad and into technical biomechanics labs. Researchers rely on embedded force pressure plates, high-speed treadmill analysis, and optical motion capture to mathematically map these skeletal forces in real time. We can see that translation happening here. This digital display shows a hexagonal radar chart mapping the kinetic data of a runner, directly informing the physical prototypes lined up beneath it. Metrics like bounce, slide, roll, and lean are extracted directly from the phases of gait. Engineers use these data points to calculate required cushioning densities, stability shanks, and the precise angle of flex grooves. It requires a rigorous working knowledge of human anatomy to accurately translate that raw motion data into the physical architecture of a functional product. When designers ignore this biomechanical reality, the physiological costs are severe. Medical data shows that roughly 70% of common foot problems stem from incorrectly designed or ill-fitting footwear. Shoes that restrict the natural flex of the tarsal-metatarsal arch or blunt the mechanical leverage of the phalanges create immense localized stress. Over time, this leads to painful pathologies like flat feet, splay feet, and hallux valgus. Today's footwear designers utilize a toolkit of CAD software, trend analysis, and material science, but those tools are ineffective if the underlying geometric structure of the shoe fails to respect the kinetic demands of human bipedalism. You cannot successfully engineer the external shell without understanding the internal engine. Success in footwear design begins with mastering the foot's complex biomechanical requirements.